Hey everyone, so welcome to the video on power series. This is our first video on power series, and as you've seen so far in this chapter, a lot of what we've dealt with so far is the question of if you add an infinite list of numbers, can you tell whether that infinite list sums to a finite value or blows up to infinity? And we've seen so many tests that help us tell whether a series converges or diverges. And we're going to use some of them in what we call power series. Now, power series are, well, as the name suggests, these are series that are formed or constructed using powers of a variable, usually x. So, for instance, you could have power means powers of x. So something like, 1 plus x squared plus x cubed, all the way to infinity, where the power is increasing at each step. Right? So that's what's called a power series. And it's actually similar to an object you've seen before, which are basically just the polynomials, right? If we say a polynomial has degree n, that means its highest power, or the highest power of x that you see, is x raised to the nth power in that expression. And it goes down x to the n minus 1, n minus 2, all the way possibly having a constant term that corresponds to x to the 0th power. And the c sub 0, c sub 1, up to c sub n numbers are called the coefficients of your polynomial. So for power series, it's really, really similar, except that we allow these polynomials to go to infinity. In other words, we don't stop at a certain power of x. We just keep going on forever. And that's why we have the sigma notation here, n equals 0 to infinity, telling us to not stop adding. So in a sense, you can think of power series as infinite polynomials, right? Polynomials of infinite degrees. And maybe you're thinking, well, therefore my polynomials, where I stop at n, these are just my partial sums, right? And you'd be correct there. This is your nth partial sum of the power series down here. And power series are useful, and you'll see some of the applications of these power series in a later section. But right now what we're concerned with is, well, can we ask the same questions that we asked before for series that didn't have a variable inside? Right? Can we tell whether these power series converge or diverge? I'll give you an example. Okay, so take Cn equals 1 for all n. Right, so I lost my text there. I'll write them all again on this slide. Okay, so if we construct a power series where we say, okay, the coefficient of x to the nth power, c sub n, let's set that to be just 1, regardless of what n is equal to. Okay, what does the power series look like here? So the power series looks like, so c0 is just 1, c1 is just 1, so it's 1 times x, c sub 2 is 1, so it's just 1 times x squared, right? And you just plug in 1 for each coefficient. And this is what it looks like. The sum from n equals 0 to infinity of just x to the nth power. And now I can ask the question, does this converge? Or does this diverge? And if you think about this a little bit, you can probably determine here that, well, Doesn't it depend on the value of x, our variable, whether it converges or diverges? I mean, what kind of series is this? This is just a geometric series. This is an example of an infinite geometric series. And your common ratio is x, right? From term to term, you're multiplying x to get to the next term. And we know exactly where geometric series converge. Therefore, this converges when the absolute value of x, which is the absolute value of a ratio, is less than 1. Which means, well, if I plug in 1/2 there for x, I'm actually going to get a number there. And I know what that's going to sum to, right? 1/1 minus 1/2, which is 2. But if I plug in something like 3, that's not going to converge to a finite value. And we can even visualize this on a graph. All right, so this is our power series, 1 plus x squared dot dot dot. And as I mentioned a while ago, well, we can actually look at partial sums here. Right? I mean, the definition of convergence for a series is the same. It's the limit of the partial sums. If that exists, then it's convergent. So let's look at the partial sums, which is just you're stopping at the nth degree term. So at n equals 0, what does your partial sum look like? Well, it's just 1, right? It's just a constant function 1. That's why you just have this horizontal blue line here on your graph. What's the partial sum for n equals 1? So it's 1 plus x. Okay, 1 plus x, that's your linear function here with slope 1 and y-intercept 1. N equals 2, so it's 1 plus x squared. Okay, that's a quadratic. And n equals 3 is a cubic. That's the function formula. That's the function graph. N equals 4, 5, 6, and what's happening here? You see that as I increase n here, the terms here in the middle, right, in between -1 and 1, seem to stop moving. And in fact, the closer you are to 0, the faster you stop moving. Whereas if you pick an x value, say at x equals -2 or x equals -1.5, what's my function value at that point? Does it stabilize to anything? No, it just keeps going up and down and up and down and up and down forever. All right, so visually, this is what it looks like when we say, well, if I plug in x equals -1.5 into this series, it's going to diverge. But if I plug in x equals 0, or x equals 0.5, or x equals -0.5, it's going to converge. So in fact, as we saw on the slides, as long as you're in between -1 and 1, you'll actually converge to a finite value. And what does it converge to? Well, again, we already saw it converges to 1 over 1 minus x in general. Right? Again, that's the formula for the sum of an infinite geometric series. So what does the graph of 1 over 1 minus x look like? It looks like this. And you'll see that in between x equals -1 and x equals 1, the power series, the blue curve, approaches the red curve. Right? So it converges to 1 over 1 minus x, the function. Right? And so this is what we're doing here. When we talk about power series, we're actually not concerned with the question, well, for what value of x does this infinite polynomial give us a finite value? So I'm just going to state here the formal definition, the definition in the textbook. A power series is a series of the following form, right? So it's a a sum involving powers of x, where for each power of x, you associate a number c sub n called the coefficient. And in fact, once you know what the coefficients are of your power series, then you know your power series, right? That's all you need. Because this x to the nth term, that's always going to be there. What matters in a power series is, well, what do my coefficients look like? So in the previous slide, we had Cn equals 1 for all n, and we had that behavior there, convergent for x between -1 and 1. Now, that was an example of a power series centered at 0, where you had the polynomial, well, infinite polynomial, or this power series, where all the terms were just x's. We can generalize this to having x minus a for each term instead. And we're going to call that a power series centered at a. Right, so a is called the center of the series. And when we look for the values of x for which these converge, that's what we're going to call the domain of the power series. Set of all values of x for which this infinite series converges. And so in the next question, in the next example here, we can rephrase this question as find the domain, right, of this function. Right? You should start thinking about this as a function of x. Right? What is a function? Well, you give me an input x, I plug it in, and it gives me an output. So the domain of the function is, remember, the things you're allowed to plug in and get a finite value out of it. So that's exactly what we're trying to do here, right? For which values of x do you actually get something that makes sense here in terms of, it's a finite value, it's a finite real number. It converges to something. So how do we do it in general, right? In this example, for Cn equals 1, we knew it was geometric. So it was very easy to do, right? We knew exactly what the behavior of geometric series are. It just depends on what the common ratio is. How about this one? It's not geometric. Well, this is where our other tests for convergence come in. And in fact, when you're testing power series for convergence, one of the more important tests that you're going to be using is the ratio test, because of this x plus 2 to the n term. Because if you take the n plus first term and you divide it by the nth term, you're basically going to be left with a single factor of x plus 2. Okay, so let's try it here. Let's try to apply the ratio test. And take the limit. And we're not just taking the limit of the ratio of the c sub n, which is, in this case, I should explicitly say, well, what's c sub n in this power series? It's 1 over n. Ooh, and I guess I should say here that we are starting at n equals 1. Because clearly at n equals 0, that's not defined. So Cn is just 1 over n for all n larger than or equal to 1. So let's apply the ratio test. Okay, so your term is this whole thing with the x. But you replace n by n plus 1. And I divide by the same term with n. Okay, so I'm multiplying by this now. And this is just the absolute value of x plus 2 times n over n plus 1. And, well, what do we do here? Well, note that this is x, right? It doesn't depend on n. So what about this term, n over n plus 1? Well, that just approaches 1. Okay, in fact, I can write it like this. Divide the top and the bottom by n. And this gives me just the absolute value of x plus 2. Therefore, this tells me by the ratio test, so what does x have to be for this series to converge? Well, it has to be less than 1, right? Whatever we get from the ratio test. This is your limit. And what does this mean? Well, this means -3 is less than x is less than -1, right? Just solving that inequality for x. Also, if x plus 2 is strictly larger than 1, then this series diverges. In other words, if x is less than -3 or x is larger than -1, it diverges. Now note that there are 2 points where the ratio test does not tell us anything. When x is exactly -3 or -1, you plug them into the limit here. They both give you 1 for the limit, which means if I had -3 or -1 here, the ratio test would not give me anything. But that's okay, right? We have other tests. At x equals -3, what does the series give you? Well, now you're actually just looking at a specific value of x. So let's just plug it in. It's -1 to the n over n. Right? -3 plus 2 is -1. And this is your alternating harmonic series, which we have already looked at before, is convergent. Whereas at x equals -1, your series is now just -1 plus 2, which is 1 raised to the n. So it's just 1 over n. And this is just your harmonic series, which is not divergent. Right? And so what do we have here? It converges for these values of x and converges at -3, diverges everywhere else. And now we have our conclusion. The domain for this power series is -3 inclusive to -1 excluded.